Hey guys, welcome to episode 0 of the mathematics series. This is the series intro or the overview. So let's just get right into it. The first couple episodes are going to be on the foundations of math. So the foundations of math include set theory and logic. So we'll start off with logic and proofs, and then we'll go into sets and classes, okay, which are about like collections of things, okay? So after we do foundations, we are going to have the material that we need to talk about structure. So mathematical structure is sets. So it's going to come from this set theory, sets, and predicates. Okay, and then we'll talk a little bit about sets and predicates, but basically sets are collections of things, and then predicates are very similar objects. There's actually the class of sets is embedded in the class of predicates. So we'll cover those. And then there's going to be this subfield down here. So let's draw this oval. And some structure, there's certain sets and certain predicates that represent relationships. Okay. So these include relations, okay, and graphs. I'm going to write digraphs. We'll get to that. Directed graphs, okay, kind of two different representations of a similar concept. And then we're going to have another subset. Let's draw this right here. Another subset of that is going to be functional structure. Functional relationships. So functional. Okay. And functional relationships include functions. Okay, see how, obviously, functions and operators. Okay. So operators and operations, that's another type of functional structure. Okay. So now we're going to have a couple different names for these disjoint subsets of structure, okay? So within this functional structure is going to be called algebraic structure. Okay, algebraic structure. So we're going to be talking about like operations, and then we're going to be talking about groups, rings, fields. This is all going to be, that's going to be abstract algebra, so algebraic. And then we'll be talking about linear algebra, so we'll be talking about vector spaces, and it's all going to be functional structure on a space. So this is all going to be algebra, linear algebra, abstract algebra, algebraic structure. And then later on in this series, we're going to go up into relationships. And then this is going to be non-functional relationships, which is called topological structure. Okay. So we'll talk about algebraic structure, then we'll jump out here into topological structure. And this includes things like graphs and relations. And particularly, we'll look at things like equivalence relations, which kind of have a correspondence between equivalence relations and partitions. and then we'll talk about ordering relations and lattices and a bunch of different things about relationships and topological structure. And then what we'll do is we'll combine these two, algebraic and topological structure, into a hybrid structure called geometric structure. Geometric. Okay. Now, geometric structure is things like measures. Okay. So measures is a very good example, or inner products. Or norms. Or metrics. These last three are very correlated to each other. Metrics. Okay. And there's plenty of other examples. So I'll write ... So measures is a big geometric. It's very geometric. It's a big geometric structure because it literally assigns a size to space. Okay. So geometry is all about, let's do a different color here. Let's do, I already used yellow. Let's use this light blue. Okay, so geometric is all about size. Geometry is all about shape and size. So I'm going to write size here. Topological structure is all about shape or space. Okay. And then functional structure or algebraic structure is all about number. Okay. So now geometric structure is what happens when you apply algebraic structure to topological structure. So you're applying numbers to space, and then you get a size. Okay. So we got algebraic structure, topological structure, and then geometric structure. We'll cover all those in three different chapters. And then there's one more category out here which we won't talk a lot about. Well, we won't talk a lot about directly outside of the first two episodes, but I'm just going to call it basic structure. Okay. So we got algebraic structure, and then this oval not including this inside is topological, and then this box that doesn't include this inside is the basic structure. And it just has to do with sets with no extra properties and predicates with no extra properties, but mostly these guys, because we like looking at sets. Sets are a little bit easier to deal with. Predicates is a little bit larger of a class, and it's not as well behaved. Okay, that's why we create these things called sets within set theory, within ZFC set theory, is because it's like a copy of a subset of predicates. Okay, so here, let me draw a little diagram. In here we have the class of predicates. In this series, I'm going to call it pred. So the class of predicates is this circle, and then there's this subcircle. Okay. Which is, I'll call it not set. Let's call it ket. I don't know. Just think of a different name, right? So there's some like subclass of predicates called ket. Okay. And this is completely identical in every way to the class of sets. Set. Okay. So set is a copy. We kind of like manually copy it with these axioms. There's quite a few of axioms in set theory, and we copy a subclass of predicates into this class of sets, and this class is much easier to deal with. There's not any contradictions. In this class of predicates, there's some contradictions and it's a little tricky to work with. So when we're working with sets, we are working with predicates. They're kind of analogs of each other. A consequence of this copying that goes on is that we're always going to have a predicate analog of every set. So that's why we have this duality here. We have relations, and relations are types of predicates. So relations live here. And then digraphs or directed graphs are the set analog of that. Okay, so it's the copy of relations onto the class of sets. So these are analogous to each other. Similarly, we have functions, okay? And then there's special types of directed graphs that are functional. So then we have functions are a subset of relations in here, and that would be a subset of directed graphs, and those are analogous to each other. And for any set that we have, there's going to be an analogous predicate, and we'll look at why that is. But that's just a little note. We say that the class of sets, or I say, the class of sets is embedded in the class of predicates. And again, we'll denote the class of predicates like this. And so that pretty much covers the types of structure that we'll be talking about. Basic structure, topological structure, algebraic structure, and geometric structure. Pretty much in that order. And then we'll bounce back and forth between some of them because we want to cover this series in the most linear way that we can. Math is kind of a tree, so you start out at the foundations of math, and then you branch out into more and more ideas, and then some ideas come together, and then it's just this huge network of new ideas always being created like this. So if math is like this, it's going to be kind of hard to follow in a straight line. So if we really want to do this in one series, we got to backtrack sometimes, and then we got to take math in a bunch of different directions. The trick is that we always have to have the prerequisite knowledge to go to the next episode. So that's what we're going to do in this series. I hope that we'll always have the prerequisite knowledge to be able to go to the next episode. I planned it that way, and I think that it's going to work out quite nicely. So let's erase some of this and talk about what we're going to be, what the episodes are going to be, okay? So the episodes, I won't tell you episode by episode, but I will tell you the chapters. So there's this episode and the foundations. I guess you could call this foundations because it's kind of the conceptual foundations of what you're going to be learning. Foundations. Okay. So foundations, and this is only going to be 2 episodes, logic and proofs, and sets and classes. Once we get out of the foundations, we are going to, it looks like we're going to topological structure. So and this is going to be about relations and graphs primarily. So this is going to be relations and graphs, and particularly we'll look at ordering relations, and we'll look at equivalence relations, and just relations in general, and graphs in general, and then we'll look at algebraic structure. Okay. Algebraic structure is going to be 7-ish episodes, so that'll be a little bit longer than the topological structure. And then we're going to combine the two into, let's see, red and blue makes purple. So then we're going to combine the two into geometric structure. Okay. So geometric structure, it's going to be simple geometric structure at first. We're going to look at orders, orders on algebraic spaces, metric spaces, normed vector spaces, inner product spaces, and Hilbert spaces. And so that's all going to be combining kind of like relations, ordering relations particularly, which is a very subtle topological structure, into algebraic structure, which is going to immediately give us geometric results of size, particularly with like metrics and stuff, of distance from each other. That's very geometric. Okay. And then we'll go back to this light blue because we're going back into topology. But here, now when I say topology, I mean the study of topology. So it's a very special kind of topological structure called a topology. The word is used a lot here. And that'll give us topological spaces and manifolds, and then we'll be able to build that up into tangent bundles and then tensors. Once we get tensors, that's going to be our segue into the purple, which is differential geometry. I'll just write diff geometry. Okay. So we cover some geometric structure over here, but then we really get into the differential geometry over here, which is applying what we know here about this geometric structure onto topology. Okay. So there's differential topology, but then we apply geometric structure to it in the form of a metric tensor, and that gives us all the notions of geometry that we know. So let's just erase a little bit of that real quick. Okay. So after differential geometry, we'll have a last 5 episodes of still purple measure theory. Okay. And measure theory is definitely geometry because it is applying size to space. Okay. It's the thing that's able to tell you, oh, this Gatorade bottle is 591 milliliters. Okay. Milliliter is a measure of space in this container. And so measure theory is all about assigning numbers to space. And that is why it's this purple geometry that we got going on here. So that's the series overview. If you like what you see here and you want to learn it, subscribe. We're going to post an episode every Monday. It's going to be Math Monday, and I might have a problem of the week at the end of the episode, and then I'll give you a solution on Solution Sunday. So if you like what you see here, subscribe, and I'll catch you guys in the next one.